Okay, so in this video, we're going to look at this complex absolute value inequality. And in doing it, we're going to use a piecewise function to represent our inequality, and then we're going to find out when is that function greater than 0 and when is it less than 0, and that's going to be how we find our solution. So the first thing we do is we establish the function by subtracting this and then adding 3, so we get absolute value of x plus 2 minus the absolute value of 2x minus 3 plus 3. And we have this function, and then eventually what we're going to do is find out when is this function greater than or equal to 0. So when is it a positive function, and that's going to be our solution. When is this function a positive? Now, functions that are absolute value can be broken into what is called a piecewise function. And the pieces of the function happen in the intervals by which the absolute values themselves are 0. So when is this one 0? It's 0 when x is negative 2. So that first absolute value, x plus 2, equals 0 at negative 2. This one is 0 when x is 3 halves. If you set 2x minus 3 equal to 0 and solve it, you get 3 halves. So our intervals for our piecewise are negative infinity to negative 2, negative 2 to 3 halves, and 3 halves to infinity. So these are the intervals that we are going to look at this function. And the reason we're going to look in these intervals is because these are the points by which the absolute values change from positive to negative. So from negative infinity to negative 2, both of these absolute values, any point in those regions, if you plug them into the inside of these absolute values, you get negative. And when the absolute value is negative, the answer is the opposite of that, multiplying by a negative. So we do negative x plus 2 minus a negative 2x minus 3 plus 3. Now we'll come back and we'll simplify that in a second. For the second interval, 0's in this interval. If you plug 0 into the x plus 2, well, 0 plus 2 is positive. So for this interval, negative 2 to 3 halves, x plus 2 is positive. So then for now, we can just say, well, that means it's just x plus 2. For the next interval, if you plug 0 in, you get 2 times 0 is 0, minus 3 is negative 3, so that absolute value is negative. So we do the opposite. So we're going to do minus a negative 2x minus 3, and then plus 3. For the last interval, both x plus 2 and 2x minus 3 is positive, so we can just remove the absolute values, and we get x plus 2 minus 2x minus 3 plus 3. Simplifying all this, first off, if you got minus and negative, those just become plus. If you've got a negative here, that becomes a plus, and both of these become minus inside there. So that's going to give you a negative x plus 2x, and so I'm going to rewrite my function down here, which is x, and then you're going to get a negative 2 minus 3 plus 3, which is going to be minus 2, so you're going to get x minus 2. And that's for this interval here, negative infinity to negative 2. And then you're going to have positive x, positive 2x is 3x. 2 minus 3 plus 3 is just going to be 3x plus 2. And then for the last one, you're going to have, this is going to be minus and plus to make that a plus. So x minus 2x is negative x. 2 plus 3 is going to be plus 8. So now, in looking at our intervals, we have this function that's only defined in each of these intervals. And to find out when is this greater than 0, we use a simple fact, and that is the truth value, so that whether or not the inequality is true, changes at the critical points of the function. The critical points of the function are when the function equals 0. So we need to go through and find out when does this function equal 0. So the function might equal 0 in this right here when x equals 2, but x equals 2 is not in this interval. And so that does not work. In this interval, you get x, this is 0 at x equals negative 2/3. Negative 2/3 is in the interval, and so this is a 0 of the function. And then finally, this one is x equals 8, which is also in this interval and is also part of the function. So the critical points, the zeros of the function, are at negative 2/3 and 8. You make a number line, placing those on there. And now the last thing on this problem is the inequality true at these three regions? And then you can do that just going back to the original inequality, plugging in a value from each of the regions and determine its truth value. So I'm going to pick -3 from this one. Is -3 true? Well, that's going to give me the absolute value of -1. Is that greater than or equal to the absolute value? Well, -6 minus 3 is a -9. Minus 3. Well, no, 1 is not greater than or equal to 6, so -3 does not work. You can pick 0. If I plug in 0, that's going to give me the absolute value of 2. Is that greater than or equal to the absolute value of -3 minus 3? Yes. 2 is greater than 0. Absolute value of -3 is 3, minus 3 is 0. So that works in this region. And then if you pick 10, it's very easy to see you're going to end up with absolute value of 12 greater than or equal to the absolute value of 17 minus 3. Well, yeah, that is false. 12 is not greater than or equal to 14, and so everything in that region is false. So the solution here is -2/3 to 8, and it is equal to, because this is an equal to problem. And so yes, it is true on the boundaries. At -2, it makes it equals to, and at 8, it makes it equal to, and then anything in between. So the solution to this problem is all the values for x between -2/3 and 8.